Okay, we're ready to begin our study of calculus now that we've got the prerequisite material kind of talked about and out of the way. We want to look at the two motivations for calculus, the tangent line problem and the area under the curve. The tangent line problem is what we're going to address here in this course, first semester calculus, sometimes referred to as the differential calculus. Most of you will go on to take Calculus 2, our second semester course, and there you'll investigate the area under the curve problem. Sometimes we refer to that as the integral calculus. And they're both related by the fundamental theorem of calculus and other relationships. Calculus itself as a subject is about 400 years old or so. You can see here the founders of calculus. I've got that in quotes because, again, developments in mathematics was gradual over time through many people. The main two, though, that kind of brought things together were Isaac Newton. Most of you are familiar with him, I believe, and Gottfried Leibniz, who was a German. And about the same time, these two essentially independently, from what we can understand, made the connections that basically created the calculus as we know it today. It certainly has undergone quite a lot of transformation since then. I've got a little chart here that talks about the two. Newton developed his method in 1666, the so-called fluxional method, but he didn't publish until 1687, and actually a more detailed one wasn't published until the 1704. From what I understand, Newton was very reluctant to publish things, and so that was sort of the delay there. Leibniz developed apparently a little bit later in 1675 his differential method, of which turns out we really use his Leibniz notation quite a bit in calculus. Newton's notations, maybe not so much. And you can see, though, that Leibniz published apparently a few years before Newton did. So there's quite a soap opera, if you will, between these two. There's no love lost between these two. They accused one another of different things. I remember reading a letter that Leibniz had written to Newton trying to get some information from him, and Leibniz included a result that he had proved in a way sort of to maybe impress Newton and to get him to be willing to share information with him. But unfortunately, Newton just responded by saying, your proof of this was so elementary, I proved it many times before. Basically just a slap in the face. So these two guys and their students and followers, so to speak, had no love lost between the two, and you can read quite a bit about that. It's kind of interesting. At any rate, this is the end of the 1600s, so getting into the 1700s, calculus began to be used, and it certainly has undergone, as I said, transformation since then. So what I want to look at is the tangent line problem to get us going, and this is the motivation that we have for Calculus 1. So we're going to look at a graph of a function, call it the function f. It's this solid curve right here. And I want to draw what's called a secant line. A secant line is a line that passes through any 2 points in the graph of the function f. Remember, for lines we need 2 points to define the line. And so we've got these 2 points here and here. The dashed line is a secant line. And first of all, what are the coordinates of this point right here? What are the coordinates of this point right here? Now notice I did not put any scale on these axes, so you don't know any idea what the numerical values are. So let's just say that the x-coordinate of this point is, I don't know, a. Okay. So what would the coordinates of this point be? Since it's on the graph of the function f, the coordinates would be a comma f of a. Now I want to talk about this point too, and the way I'm going to do that is I'm going to think about this point as the x-coordinate of this point as being some fixed distance from A. In fact, I'm going to let that distance be called h. Some books and sometimes you'll refer to that distance as, it's basically the run of this line. We talk about slope, right? The rise over the run. We're actually falling here, going down as we move from left to right, and then over, right? So this change in x, sometimes called delta x, I'm going to just call it h instead of delta x. That's the horizontal change. And so this x-coordinate is just going to be a plus h, right? A plus whatever h is. So assuming, again, h is positive, will be on this side, and the coordinates of this point, a plus h, comma, f of a plus h. Okay. Now, the question I'll have for you is, what is the slope of this secant line? We have the slope. It is the vertical change, as we said, over the horizontal change. And the vertical change is just the difference in the y-coordinates of these 2 points. So I can take the y-coordinate of this point and subtract the y-coordinate of that point. And divided by the horizontal change. But remember, we said the horizontal change was just h, right? A plus h minus a is just h. Right? And this, it should look familiar. This is the difference quotient we've talked about, and we will continue to talk about. Difference quotient gives you the slope of this secant line. This quantity also represents what we call the average rate of change of the function. If you remember from pre-calculus, the average rate of change of a function going from a to a plus h. All right? Now, this is the secant line problem. This is pre-calculus. Give me 2 points. I can find the slope. I can find the equation of the line, and we're good to go. So I can take any, if I give you a particular function and a value of a and a value of h, you will be able to compute the slope. Right? But the question is tangent line. Well, now what's the tangent line? Well, right now we're just going to sort of give a squirrely little definition here. It's not going to be mathematically exact, but tangent line is a line at one point on the graph, and it's the line that we say just touches the graph at that point. It doesn't pass through the line at that point. Let me give you an example at A. So what would the tangent line at A look like? I'm going to use this pink ruler, straight edge here. The bottom of it is going to be the tangent line. Now, tangent line is not going to be something like this, passing through this point A, because it passes through the graph locally, right there. So we want it to just barely touch the graph, and I kind of drop down so it just touches one point locally. Now, it may intersect the graph. Notice the function continues to rise up here, so we might intersect up here, right? But locally, real close to A, right? Then this is the idea of the tangent line, where it just touches the graph there. Okay, so what would that line look like? It's going to be maybe something like this. Here's our tangent line. Okay. Another way of thinking about this tangent line, I don't know, in an application, imagine that this curve represents a roller coaster that you're riding on. This roller coaster. And let's just suppose that you're riding the roller coaster, but somehow you don't have your seatbelt on. And let's say just at the instant this thing is going up at this instant, as you make this turn, right, and begin to go down, that you escape from the roller coaster, right? The roller coaster is going to continue on this curve, but if you were to launch at that point, right, your momentum would carry you along a line, right? From if you escaped right at that point, and that line you would ride on would be the tangent line. Granted, now you might have some gravity that will change and bring you down, but assuming, let's say you're on a space coaster, you're in outer space, right? And you launch from that roller coaster, as it rolls around here and you separate from it, you would continue on that line. That's sort of a tangent line. So again, it's not a very good definition yet, but we need to develop this, and we will. So Graphically, though, how can we estimate this? How can we find the slope of the tangent line? I only have one point, right? I don't have another point. There's, I can't find another point here. So how are we going to find the slope of the tangent line? That's the tangent line problem. So here's what we are going to do. We are going to estimate the slope of the tangent line by the slope of the secant line. You say, well, that's pretty lousy. The secant line here is obviously got a negative slope, whereas the tangent line has a positive slope. Well, the idea is I can get a better estimate by letting the value of h get closer and closer to 0. Let delta x get smaller and smaller. As we do that, right, this point is going to move to the left, and this point on the curve is going to move to the left, right? So as h gets smaller, maybe I'm going to be somewhere right about here, right? And then my secant line would look like this. Right, there would be my secant line, right, passing through the point this way. Right, if I got the point here. But I can get this point closer. H would now be from here, right, to here. H would be this little short distance here, would be H, right? But let's let H be smaller, right? So now the point comes up here to this point. And now our secant line looks like this. Right? Now notice the slope is going to be positive, slightly positive, right, for this secant line. But we can get even closer than this point, right? I can get up to, say, here. And now my secant line will look like this. Right? But do you see what's happening? As we move, right, through this sequence, right, the slope, look at the bottom of the pink straight edge here, these secant lines are getting closer and closer to that tangent line, right? And therefore the slopes, right, are getting closer and closer to the slope of that tangent line. As we get closer and closer, right, how close can we get? Well, we can get as close as we want to. We can just keep letting h get smaller and smaller. Now we can't let h be 0, right? The minute we let h be 0, we've got a problem. We can't divide by 0 here. The slope of the secant line would be undefined. So we always have to have a very small value of h, but we can make h as small as we want, really, really small, infinitesimally small, we say. And as we do that, right, then we're getting closer and closer and getting a pretty good approximation for what that tangent line slope is. So if I think about this slope as a new function, say, of h, g is a function of h. If I were to graph g as a function of h, what would the graph of g of h look like? Let's graph the function g of h down here, right? Well, what would happen is, I would measure the slope when h was some positive difference here, right? Then we're looking at this original secant line, which has a negative number. So if h, let's say, I don't know what that is, the h value is some positive number, then we're some negative value down here for the slope. As h gets smaller and smaller, the slopes of these secant lines, as h gets smaller and smaller, begins to get less and less negative, right? So here we are on the original one. As we move to this one, we're still negative but less negative, right? So we continue to sort of move closer and closer. In fact, somewhere right here, if we choose a point that is at the same height as the value at a, our secant line will be horizontal. It will have a slope of 0, right? Slope of 0. And as we continue, right, we continue to move, right, closer and closer to 0, what's going to happen? The slope becomes positive, right? The slope becomes positive for these lines. And then what? We're getting closer and closer. Right at 0, when h goes to 0, we're right at a. What's this expression going to be? It's going to be undefined. So graphically, what we're going to see is, right, when h is 0, we're going to see a hole, right? So if we continue this, we get this graph of the slope that might look something like this. So this is the slope of the secant line. right, at a given value of h, right? When h is 0, we're here. As gets more and more positive, we're moving away. I could even let h be negative, and I've even indicated what the slope would look like there, right? If we were back here, if we pick a point down here, if h is negative, we will have a slope that's positive and more positive than our tangent line. Okay, but here's the idea, and so we're going to be looking at this process, and this process here is the process of finding what we call a limit. And so let's look at that. Our doorway into calculus is this idea of a limit. So what is this all about? So the tangent line problem we'll come back to. We'll be able to define it after we discuss limits. Okay. So what I want to do is I want to consider this function here. First of all, this function here, what's the domain of this function? What's the domain of this function? The domain is what? All real values of x, such that x cannot be what? 2, right? Can't divide by 0, so x cannot be 2, right? What does the graph of the function look like near x equal 2? Now, some of you might think of, hey, there might be a vertical asymptote there, okay? I'm going to use technology to help us out here and just plug in values of x close to 2. And I'm going to enter in this function, x to the 4th minus 16. Notice that's in parentheses, divided by x minus 2. And I'm going to use the table feature, and I'm using the 83 here, the 84 is similar. I'm going to use the table feature. You see table over here, up above the graph key, and TBL set, that means table setup. So I'm going to do second and press the window button to get to my table setup. And I'm going to make sure I'm in ask mode for my independent variable. And the dependent variable I'm going to leave in auto mode. So let's see what we get here. When I plug in, let's see, got that independent variable in ask mode. Okay, so why is it not doing the right thing? Oh, okay, let me delete those values. I'm sorry. Okay, now I'm ready. I want to see what's happening as I get close to 2. So what number, close to 2? Well, 1.5 is close to 2, and I get this value for the function. I can get closer to 2, right, by letting the x value be 1.9. What's closer to 2 than 1.9? 1.99. What's closer to 2 than that? 1.999. You get the idea? I just keep getting close. How long can I do this process? I can continue this basically forever, essentially, mathematically, right? Getting closer and closer to 2. And you can see the values of the function. Now, what do we have? Do we have a vertical asymptote? Well, I don't think so, because the values are not becoming unbounded, right? They don't seem to be going, like 100, 1,000, a million, a billion, like we would have with a vertical asymptote. So let's also look from, if we were to look from above 2, a little bit bigger than 2, like 2.5, 2.1, 2.01, and so on. I can get closer and closer to 2 from above, so to speak, from values of x greater than 2, and we're getting closer and closer to something. And I've filled this out in this table here. All right. Notice as x gets close to 2, what is the value of the function getting close to? Notice how I've done this table. I've got these values of x. I'm getting closer and closer to 2 as we go toward the center of the table here. So the functional values are getting closer and closer to what? Seems like somewhere between 31.998 and 32.002, which we might say it's close to 32. Maybe it's getting closer and closer to 32. Right? We say that the limit of the function as x approaches 2 is 32. So the limit is basically, what is the function trying to get to? I can't plug 2 into the function. It's undefined, right? But it seems like as we get closer and closer to 2, the value of the function is trying to get to 32. It's trying to approach 32. Shorthand notation is LIM for limit, and then underneath we'll write the variable x, right, with an arrow and then 2. X is approaching 2. We say the limit as x approaches 2 of the function is equal to 32. Or the limit as x approaches 2, we can actually write the entire rule for the function is equal to 32. Now, let's graph this function and see what's happening. I'm going to graph it over the interval from x going from 0 to 4 and y going from 0 to 40. So I'm going to adjust my window settings here. I'm going to go x from 0 to 4 and y from, from 0 to 40. I'll do the y scale at maybe 5. The y scale and x scale are just the distance between the tick marks on your graph. And let's take a look at the graph. Okay, and what do you see here? Let's go to trace, right? We can see x is 1.74. Here's the y value, and there's the point. As I get x closer and closer to 2, look at the y value. Again, it's getting closer and closer to maybe, like we said, 32. In fact, when I hit exactly 2, look at the y value. There is no y value. Again, it's undefined. Look at the graph. What do we have there? We have a hole in the graph. Okay? And we talked about that hole a minute ago when we were talking about the slope of the secant line. And so the same sort of phenomenon. Now, when we draw a graph like this, right, how are we going to draw that? We're going to draw that graph and exaggerate that hole. We're going to exaggerate that hole. So right there at x equal 2, we will have the value of 32 apparently. That's what the function is trying to get to, right? As we approach from either side, right? As we get close to 2, as x gets close to 2, the value of the function is getting closer and closer to the y value of this hole, which apparently has a value of about 32, right? That's the height. That's what it's trying to obtain. Okay? So limits are going to be involving a lot of times functions of this nature. And in general, we don't have the question of what's a function trying to obtain. What's it trying to obtain as it gets close to 1.99? Well, I know at 1.99 it's trying to obtain that value there for this particular function, it turns out. But we'll see that the value of the function at 2, for instance, does not really necessarily have any bearing on the limit of the function as f of x equals 2, and we'll talk more about that. So here's the intuitive definition for the limit. If the function f of x gets arbitrarily close to a real number L, which was like our 32 up above, as x approaches or gets close to a, which was like our 2, then we write the limit as x approaches a of f of x as L, or f of x arrow, which means approaches L as x approaches a. And the phrase gets arbitrarily close to means basically as close as we like. So going back to that example here, I can get as close to 32 as I want to by letting x get closer and closer to 2. Right? The closer and closer I get to 2, the closer and closer the function will get to the value of 32. Now, if you're a math major, you would probably want to be interested in a more rigorous definition of this gets arbitrarily close to so-called Epsilon-Delta limit definition. And the book does talk about that, and you can look at that. Now, if the function f of x does not get arbitrarily close to a number L as x approaches a, then we say the limit does not exist. It is possible for a limit to not exist, and we're going to talk about that. When I have a limit that does not exist, I'm going to write DNE from now on. So, now, again, I mentioned this already, the value of f of 2 does not exist in the previous example, right? It was undefined, but the limit does exist. For a limit to exist at a, the function does not have to be defined at a, right? We see that. There can be a hole in the graph. Okay? All right. So that's just sort of the brief introduction to the idea. What we want to look at now is, in the next video, is looking at limits numerically and graphically. numerically and graphically, and that's where we'll start our journey of limits.